river event. So thanks for joining this final session on the VC Atmospheric River event. The first speaker in this session is Lisa Malonina. Her title is Human Influence on the 2021 VC Floods, Attribution of Extreme Precip. Go ahead, Lisa.
Okay, do you see my screen?
Yeah.
Perfect. Okay, good morning, everyone. As Nathan said, I will be talking about the human influence on 2021 VC floods, and particularly the extreme precipitation aspect of that event. So what I will be talking about is the part of the rapid attribution study, which was led by Nathan and published early this year in Weather and Climate Extreme Events Journal. And as I said, I will be talking about the extreme precipitation aspect of that, extreme precipitation part of that study. And just to remind you, I'm pretty sure you're aware by now, but the precipitation was brought by a westerly oriented atmospheric river. It was the main reason of the flooding, and the resulting flooding was the costliest natural disaster in BC history and maybe in Canada. So the questions which I'll try to answer now: what the scale of the event, how unusual was it, and did the human-induced climate change impact or change the probability of that event, and what do we expect in the future? So here, this slide, you can see the cumulative precipitation from Era 5 in southwestern BC from the 1st of October until the end of November. And the 2021 is the red line here. And so what you can see that the red line lies kind of in the upper half of this cloud of the gray lines. Basically, that means that October and November period was quite wet generally. And here, the steep increase in the precipitation is the 14th, 15th of November. And this is exactly the time when atmospheric river made a landfall. For that reason, I will be talking further about ARIX today, so maximum consecutive two-day precipitation. However, it's important to note that most of the precipitation fell between the midnight on the 14th of November and midnight on the 16th. So that means that the values are already, they are very nicely distributed in between these 2 days. And so if we will be looking at ARIX 48 hours, it won't be the same results. But since ARIX today is generally quite commonly used value, I will be continuing with that. So here you can see the ARIX todays from observations. Here you can see probability density function, GV return period curves, as well as observational time series from Era 5, the blue one, and Kappa 10 kilometer one product in brownish color. So we estimate return periods to be 45 years from Era and 100 years from Kappa. And if you look at the time series, you will see that 2021 was not the largest in Era. It was preceded by 3 other years, 1955, 68, and 2003. However, in Kappa, 2021 is the year of the maximum of ARIX today. And so another feature you can see is the fact that in Kappa, the values are much higher than in the Era. And yesterday, I don't remember who was the speaker, but people in the this session was addressing this question, and actually we came to the same conclusion, that this difference actually comes from nothing but basically just the resolution of the two products. Because Kappa is better resolved than Era, it can capture the smaller patterns in the observations better. To analyze how humans influence the probability of the event, we analyzed 22 Synoptic models, and the results are presented here. So you can see probability density functions, QQ plot, which shows the goodness of the fit, as well as return period curves over here. The red solid line shows era 5 value for 2021, as well as the dashed red line shows maximum era 5 value, which was 1955. So the green line shows the values for the pre-industrial climate, so 1850 to 1900. Orange is the current climate, so 2011 to 2030 values were considered, and the blue colored are the values for the end of the century under SSP 2.5 scenario, which considers 2.7 degrees warming. So if you listened to my talk yesterday about the heat wave, you might remember that the distributions there were so nicely moving to the right. Here they are not, the changes are not as drastic as the full heat wave, but we still can see that the distributions are moving to the right, which basically means that the extremes are getting stronger with warming climate. And if we look at the increase of the probability over here for the 2021 event, we will see that it's a factor of 1.5 increase for current climate in comparison to the pre-industrial. And for the SSP 2.5, there is a factor of 2 of the increased probability, but it's in comparison to the current climate, and for the pre-industrial, it will be more than a factor of 3. So in the paper, we were looking at so-called antecedent precipitation index, and for the paper, we were looking at that because it was the theory was tested that it was generally, as I said, it was generally quite wet year. And so the antecedent precipitation index was used to look how wet was the soil prior to the event. And so you can see that before the 14th, 15th of November, the values were quite high, but of course they peak after the event or during the event by its end. And actually the API here is the highest for October-November period. So if we look at the time series of API maxima, so it's important, it's not prior to the event, it's the API maxima. We will, from era 5 and kappa, we will see that for here also like probability density functions, return periods, and the time series. We also will see that by era, it was not the year, it was the 5th in the row, but for kappa, it was the year. And the return periods which we obtained were 20 years from era and 60 years from kappa. So talking about the human influence on the changes of probability of API, you can see here the same 22 synaptic models as for the precipitation, but here is the API shown. So you can see as well as prior the 2021 value from era shown in red line. And you can see here that the distributions are moving even less than for RX today. And actually the increase in probability is only 25%. And if you look at the confidence intervals, you will see that the lowest bound is actually negative. So it's not as I'm not as confident that the of the increase of that changes the probability density function. However, by the end of the century, there's an obvious increase in the probability, and it is the factor of 2 in comparison to current climate, and here the confidence interval is positive, so it's quite a sure thing. So with that, I'll leave you with my conclusions. The RX today for precipitation was 150 to 100 years event. The human-induced climate change increased the probability of RX today event at least as rare as 2021 by 45%. And this probability will increase by another 200% by the end of the century under SSP 2.5 scenario. API maximum is rarer. It's less rare. I'm sorry. It's 7 a.m. in the morning for me. So the maximum is API maximum is a 2060-year event, and the human activity increased the probability of it by 25% and will increase by another 200% by the end of the century. I will be happy to take questions, but there is the whole block of my colleagues coming after that, so they might answer the questions which you have now. Thank you.
Thank you very much, Lisa. So questions for Lisa? Please go ahead and put your questions in the chat. Maybe I'll go ahead with a question. So on the topic of the relative size of the extreme in Kappa versus era 5, I mean, it is. Can you comment on the differences between Kappa and era 5 RX2 day prior to 2021 versus 2021 itself?
That's a good point. So yeah, like if I'll try to share the screen again. Prior to that, prior to 2021, actually, on most of cases, Kappa was lower than era, and except of couple years when the values were the same. So honestly, I'm not sure what the deal is exactly with 2021, why it's so much higher. But as you might remember, we were testing even the fact that maybe Kappa is just wrong. But no, it's not. It didn't seem to be the case. So I suspect it's maybe just like how RX today like was induced, so to say. Let's say it's so as I told, like RX today was caused by this by the atmospheric river westerly oriented. So maybe the previous years were not caused by the same kind of orientation of the atmospheric rivers, or not by the atmospheric, well, most likely by the atmospheric river. But so maybe it's just an orographic kind of effect from how basically the air mass entered the Fraser River. But honestly, it's a speculation. I can't answer with big confidence.
Sorry about that. My Zoom connection dropped out for a minute. Okay, we will move back on to the next speaker now, which is Alex Cannon. His title is Reconciling the Discrepancy Between Rarity of the Atmospheric River and Rainfall Associated with the November 2021 flooding in Southwestern DC. Go ahead, Alex. Thank you.
Thanks very much, Nathan. Yeah, so as Nathan mentioned, I'll be presenting a short extension to the work that we did in the rapid attribution study. It'll be focused on trying to figure out why there's a difference between the rarity of the atmospheric river, which we characterized in terms of horizontal moisture flux, which was about was an above average event, but not all that rare. Whereas the rainfall that was associated with the event, as Lisa mentioned, was about a 1 in 50 to 1 in 100 year event. Okay, so just summarizing what I just said here. So if you look at the atmospheric river in terms of the horizontal moisture flux, or in this case, the total integrated vapor transport, we see that the magnitude of the atmospheric river was just about a 1 in 3 event if we look at it historically in the Era 5 record. If you break that down to just looking at atmospheric rivers with a more zonal orientation, so we've heard during these sessions that the atmospheric river had a more favorable orientation for pushing moisture up the Fraser Valley. So if we just isolate kind of zonally oriented atmospheric rivers is more intense, so about a 1 in 10-year event. Whereas the 2-day rainfall, the RX 2-day, was about a 1 in 50 to 1 in 100-year event. So why do we have this discrepancy? So what I'm plotting here is the relationship between the storm total IVT, so that's the horizontal moisture transport, versus storm total precipitation. And you can see that there is a positive association between those, as we would expect. But the correlation is not that great. So if we just look at the magnitude of this particular atmospheric river, which was about 6 times 10 to the 7th kilograms per meter of total integrated vapor transport, you can see that there's a wide range of storm total precipitation associated with that atmospheric river's strength in the historical record. So the question then is total IVT then a good measure of atmospheric river storm severity, in particular if we're interested in looking at the impacts of an atmospheric river storm? And clearly the answer here is probably it's not a great metric. And it's not just an academic question. It's kind of interesting that about a month after this event, there was a news article that was released in California, basically, that raised this exact same point. One of the quotes in this article basically says that no dam operator or public works director is going to make a decision based on an atmospheric river category or moisture transport. What's really important is how much it rains, not how long clouds are over you. So we know then, it's not rocket science that rainfall, is not fully controlled by the amount of moisture transport. It's really the amount of moisture that's converged. So if we switch to looking at the horizontal moisture convergence, we get a much different picture. So what I'm showing here is a time series of RX 2-day, so the 2-day precipitation that that Lisa was talking about in blue, and then the horizontal moisture convergence, so basically the convergence of IVT during the storm in red. And you can just squint and see that the correlation between these two quantities is much, much higher. So it's, R is about 0.92 here. So if you characterize these events in 2021 based on horizontal moisture convergence rather than moisture transport, you get return periods that are essentially identical to those of the 2-day precipitation, so about 45 years. And the sampling variability associated with this estimate is pretty much identical to that for 2-day precipitation too. So essentially this kind of resolves that discrepancy. So horizontal moisture transport, which is typically used to rate the severity of atmospheric rivers, doesn't really tell us necessarily all that much about the ultimate impact in terms of rainfall. So one thing you'll notice here on this plot is that there's an offset between the estimated precipitation and the IVT convergence. And the reason for that is that not all the moisture that converges ends up falling as rain. Some of that moisture goes towards moistening the atmospheric column if the column is not already saturated. So can we use that information and come up with a metric that better is associated with atmospheric river rainfall? The answer to that is yes. So a number of the people who have spoken in the session put out a really nice paper last year, so in November, where they looked at something called the primary condensation rate, which is under some fairly general assumptions that are usually met during atmospheric rivers, a very good proxy for precipitation rate during an atmospheric river. So the calculation is fairly straightforward. You start with the same quantities that we would normally use to characterize an atmospheric river, namely integrated water vapor and integrated vapor transport, IVT, which I was just talking about. You define the column relative humidity, which is just a ratio between the actual integrated water vapor and a saturation integrated water vapor. And then this primary condensation rate is basically just a function of those two things. So it's a function of IVT convergence with a discounting for the fact that the column is likely not already saturated. So if you put all this together, ideally what you have is a quantity that gives you a direct estimate of precipitation that falls during an atmospheric river. So how well does this actually work? it turns out it works out really well. So what I'm showing here is the magnitude of the storm total precipitation during the strongest atmospheric river in 2021. So here's the area that we were interested in for this rapid event attribution study right here. And then if you look at the diagnosed precipitation just using this PCR, you get a spatial pattern that looks pretty much identical. So the correlation is pretty high, it's about 0.8. If you looked at the same map looking at just total IVT, you get a correlation of about 0.3. So the discrepancy is quite large in that particular case. So if we just look at this box here and we look at the time series and correlate that with the actual storm total precipitation in era 5, we see that there's pretty much a one-to-one correspondence. So storm total primary condensation rate is pretty much a perfect proxy for storm total precipitation during these atmospheric river events. And if you compare that to what we saw before for the storm total moisture transport, you see that it's a much better proxy. Okay, so we can do that same calculation then over the entire domain. So I'm just showing the correlation between two quantities here. So in the left-hand side, it's the moisture flux, or TIVT, versus precipitation. And in the right-hand side, it's primary condensation rate versus precipitation. And so you can see here that the correlation between PCR and precipitation is almost 1, especially right along the coast here, whereas the association between moisture transport and precipitation is fairly low, except over California, which is where the atmospheric river rating scale was originally developed. So the fitness for purpose in California is probably reasonable for that particular measure, but over most of the domain, it's not. One thing you will note here is that the relationship kind of breaks down as you move further inland, especially over mountainous regions. And one of the reasons for that is because some of the physical processes like hydrometeor drift, which may be important in generating precipitation in atmospheric rivers downstream, is not taken into consideration in this very simple calculation. But along the coast, it's quite a good proxy for atmospheric precipitation. Okay, so that was all in the historical climate. What if we turn ourselves to looking at simulations and future climates? So I'm going to show just one slide here that looks at a 50-member ensemble of the Canadian Earth System model, downscaled by the Canadian Regional Climate Model. This is some of the simulations that kind of underpinned the attribution work that we did in the paper. The interesting thing here to note is that this is a higher resolution product than a global model, so it's about a 0.44 degree grid spacing, which is a little bit coarser than ERA 5, but on the same order. So what I'm going to be showing you here is how different quantities, including horizontal moisture transport, precipitation, and primary condensation rate, scale with global warming. So one of the things that we'd like to do is be able to say, well, given 1.5 degrees of global warming or 2 degrees of global warming, how much will atmospheric rivers strengthen in the future? And so that's kind of what this plot is showing here. So what I'm showing right now is just the horizontal moisture flux, so the TIVT quantity that we used in the paper. And you can see that over the region that we were interested in, there's about a 10 to 15% increase in horizontal moisture flux per degree Celsius warming, averaged over the globe. However, if we look at the scaling of precipitation diagnosed by CanRCM4, we see a much different picture. So there's a lot more spatial variability, and the magnitudes are greater in many locations. So if you compare this particular plot here with the one on the far left, you can see that these don't really look the same. So if we were trying to say something about how atmospheric rivers will change in the future, and we wanted to know about impacts, just looking at moisture flux would not be necessarily a great idea. If you look at the correlation between primary condensation rate and precipitation, there's a much better correspondence. So it's likely a better way to look at atmospheric rivers, at least from an impacts perspective. Okay, so just to sum up, there's a relatively poor correspondence between moisture flux and rainfall during atmospheric river events along the coast of BC. As has been noted for a long time, rainfall is much more correlated with horizontal moisture convergence. If you want to get an even better proxy for precipitation, primary condensation rate seems to do a really good job, especially right along the coast. And I can foresee this being quite an interesting diagnostic for climate model analyses. One of the reasons for that is because of the way that PCR is calculated, you can really kind of tease out the influences separately of changes in thermodynamics. If you look at, just temperature and humidity versus changes in dynamics. So the changes in the U and B components of wind. So that's kind of the next thing that will be on my radar when I try to extend this analysis. So thanks very much, and I'm happy to take questions.
Thank you, Alex. We'll go ahead with questions. There are already some questions in the chat. So the first question is from Alyssa Steves. Are there any PCR forecasting products available?
I think Ruping would probably be better to answer this. I mean, one of the points that Ruping made in that paper is that for forecast applications, you already have QPF, you have quantitative precipitation forecasts. And so that's probably, the better way to go, because that incorporates obviously a lot more physical processes. This is really designed just to isolate precipitation due to horizontal moisture convergence during atmospheric rivers. So it's really trying to dig into that one particular process, which happens to be the one that is typically the main driver of rainfall. Okay,
thank you very much. Well, there's a related question here. Your answer to the first question probably answers this too, but this question is, what is the S2S predictability of PCR? Any work thoughts on this? So that's asking, I guess, about subseasonal to seasonal prediction.
I have no idea. Others would be much more able to answer that. That's not something I look at. So.
Okay, a last question from Ruping Mo. PCR is related to instantaneous precipitation rate. To compare with the total precipitation, you need to integrate with time. What is the time interval you use for the integration?
Yeah, so this was a 2-day integration to match up with the RX 2-day rainfall that we used in the paper.
Great, thank you very much. Okay, with that, I think we're pretty much on schedule to move on to our next talk, which is by Marcus Schnorbus. His talk title is Extreme Streamflow Associated with the 2021 BC Atmospheric River Event. Go ahead, Marcus. Thank you.
Yes, good morning, everybody. Thanks, Nathan. Again, I'm going to be presenting some material that was part of the same rapid attribution study that both Lisa and Alex mentioned, that Nathan was our leader. So we'll be talking about the extreme streamflow associated with the 2021 British Columbia Atmospheric River Event. As has already been mentioned, obviously the 14th, 15th of November saw a very large atmospheric river strike the southwest coast of BC, bringing record or near record rainfall, and associated with that was obviously a widespread incidence of flooding. We had many incidents of rivers carrying a tremendous amount of water, resulting in considerable erosion and bad movement, which caused damage to a number of highway bridges and water conveyance structures. We had a number of locations where the river exceeded its banks, occupied its floodplain, causing flooding in places like Merritt, and in other areas, obviously, where drainage is poor, such as the CMOS Prairie. We also had incidents of large and damaging floods. So this talk will just talk a little bit about, not so much obviously about the precipitation, which has been covered, but some of the other drivers, if you will, that are associated with the streamflow, and to sort of attempt to characterize the streamflow and understand sort of the mechanisms behind what caused such large extreme amounts of streamflow that resulted in such tremendous damage in this region. So to first start with, I'm going to characterize the event, do a bit of a sort of run through in time. And what we have on the chart on the left, there's 3 panels. And what this is looking at conditions in the Chilliwack Basin, which was in is a windward basin, windward of the Cascade Mountains. It's a small tributary that drains into the Fraser in the lower mainland. And we're looking at temperature, snow, and precipitation data, which is the top 3 panels, and those are taken from an automated snow weather station, which is run by the BC Ministry of Environment. And there's an image on the right that gives an indication of what sort of station it is, what it looks like. And the bottom panel is a Streamflow, which is collected at a hydrometric site near the outlet of the Chilliwack at Vedder Crossing. And I'll see if I get my laser pointer to work here. So the top panel, again, looking at the black line is cumulative precipitation, and the blue bars are precipitation. And obviously, and so what we have is beginning about the 14th, over a 48-hour period. You can see there was a considerable amount of precipitation that was associated with the landfalling atmospheric river. And we have a large increase in cumulative precipitation, in this case, of roughly 200 millimeters sort of over this 3-day period. If we go below that, what was associated with that, actually we go to the third panel, and what we see is, as is typical of many atmospheric rivers, the atmosphere is not only moist, it's very warm. And as that atmospheric river made landfall, temperatures at this particular site, which is just shy of 2,000 meters above sea level, rose almost 8 degrees Celsius and peaked at just above 5 degrees Celsius. And so there was very rapid warming. Associated with that rapid warming, in this panel here, we see initially with precipitation, we saw a bump up in snow water equivalent, but once we hit very warm conditions and the snowpack reached 0 degrees in saturation, we had very rapid melt. And this black line shows a very precipitous decline in snow water equivalent, and then the blue pulses here show the hourly melt rates associated with that. So we have 2 things. We have a tremendous amount of precipitation associated with this event, and that is then augmented because of the warming by a substantial amount of snowmelt as well. And that is mainly due to the increase in temperature. As you can see, there's maybe a few hours of delay, but associated with this precipitation and snowfall, you see a very rapid increase in streamflow, which peaks just shy or in the evening of the 15th local time, and that essentially coincides with the cessation, or as the atmospheric river is passed, precipitation stops, temperature drops, snowmelt stops, streamflow begins to decline. So to sort of summarize that, streamflow is generated by precipitation, but augmented by snowmelt, considerable snowmelt at this particular site. Over a 48-hour period ending on midnight on the 16th, there was precipitation was 136 millimeters, and total cumulative precipitation, which includes snowmelt, was precipitation was 136. Melt and precipitation, 136, 232 millimeters. Total cumulative was 368, and of that, 37% of it was actually snowmelt. So that's a considerable amount of snow. Of course, this ratio varies considerably, which we'll see in a few slides later on. You've seen this slide already, so go over it quickly. This is just trying to give an indication of antecedent wetness. Again, on the left is cumulative precipitation from Kappa, showing a number of different traces. 2021 is outlined in red. November 15th or November 14th is about where I've got my pointer, which indicates very high antecedent moisture, a very wet fall. And again, if we look at the antecedent precipitation index prior to the event, also very high, which is a proxy for very high soil moisture, which would suggest that prior to this event, watersheds were already very wet, had limited storage, and therefore were unable to store a tremendous amount of moisture, and which would suggest that a lot of precipitation would then just be converted directly to runoff. Next, we'll look at antecedent snow water equivalent. So this just shows from a number of snow pillow sites from the automated snow weather system in BC and from the snow telemetry network in the United States. Each dot represents a snow pillow. The size of the snow pillow represents the magnitude of snow water equivalent, and the color represents its probability of exceedance. I believe the record here is about 20 years. What you can see is in the sort of main area that's impacted, the probabilities are in the 60 to 80%, so not extreme, but certainly above normal. So prior to the atmospheric river making landfall, there was widespread snowpack within this region. And the magnitude was above normal, not extreme, but above normal. More directly relevant, I guess, to streamflow is the actual contribution from snowmelt itself. And here we see snowmelt rates, and the data are from two sources. The points represent snowmelt rates from, again, snow pillow sites. And this is over a 48-hour period ending on the evening of the 15th. And the background grid is from the NOAA snow data assimilation system, which is essentially a simulation system that models snow conditions on an hourly basis. The data are released almost 600 UTC every day. So this shows 48-hour snowmelt totals. What should pop out is snowmelt rates are obviously the highest here on this sort of band, which is windward of the North Shore Mountains and windward of the Cascades. And in many, in a lot of this region, melt rates exceeded almost 100 millimeters over the 48-hour period, which is considerably high. The spatial pattern between the snow data simulation system and the pillows is reasonably consistent, although it is some suggestion that the snow data may overestimate melt rates quite a bit. But obviously, it's sort of along the axis of the event, we see very high melt rates windward. As we head farther north into the coast mountains and farther leeward in the Cascades, there is still high melt rates, but they drop quite a bit as we move further inland. Although it was snowmelt obviously still contributed, there's quite a strong gradient between windward and leeward. Also, the widespread melting is a clear indication that the freezing level is quite high, which sort of reinforces the fact that much of the precipitation during this event likely fell as rainfall instead of snowfall. Another way to look at this is, again, we're looking at the snowmelt contribution. Now we're looking again just at snow pillow sites. One thing I'd like to point out here again is the main contribution was again sort of along this band here. Just to run you through it, effective precipitation, which is precipitation plus snowmelt, is the size of the dot, and those values are again highest here in this sort of leeward band that's sort of around the axis of the atmospheric river, if you will. And the color represents the ratio, the proportion of snowmelt to precipitation. And again, they're fairly high. In excess of 10% in most of these areas, but there's a few locations where they're in excess of 25%. So rather reasonable, significant contribution of snowmelt. As we move farther north into the coast mountains, we see absolutely no real snowmelt contribution as we move further north. And as we move again leeward, the ratios get higher, but the total amounts are quite small and quite modest. We're going to take a slightly different view or a different perspective on Streamflow here. We're going to look at something that we call runoff efficiency, and we're going to look at it for 6 basins. The 6 basins are the Nooksack, which is drains sort of the west or the windward side of the Cascade Mountains and Mount Baker, and drains to the Strait of Georgia just south of Bellingham. The Chilliwack River and the Coquihalla, these are sort of 3 windward basins. And then we'll also look at the Coldwater, which drains north towards Merritt, the Tulameen, which is a tributary of the Similkameen, which is gauged at Princeton, and then the headwaters of the Similkameen, which is also gauged at Princeton. So one of the things we pondered is, again, as we were moving through this rapid attribution process, we had sort of an atmospheric river event that itself wasn't unprecedented until we sort of teased it apart a bit. As Alex mentioned, we had rainfall that seemed to be precipitation that seemed to be more extreme, and then at the far end we had this extreme streamflow event that was blowing out bridges and infrastructure everywhere, and we were trying to figure out, it didn't seem to jive. So you're trying to figure out if the 2021 event from a streamflow perspective was truly an anomalous event, or if it was fairly consistent with other events in the historical record. So what we've plotted here for those 6 basins, with the windward basins arranged on the top and the leeward basins arranged on the bottom, is a plot of 48-hour precipitation, which is the x-axis, versus 48-hour normalized discharge. That's the scatter plot here, and the size of the dot represents what we call runoff efficiency, which is essentially just the ratio of discharge to precipitation. A higher runoff efficiency would imply that more precipitation during the event is converted immediately to discharge, which would imply a very wet basin, possibly a contribution from snowmelt. And at the other end of that, low runoff efficiency would suggest a basin that is dry, has lots of storage capacity, such that a lot of the precipitation won't actually make its way past the gauge during the event. So I think we see a couple of things here, and also the red dot represents the 2021 event, and the blue are the highest precipitation events. These are the upper quartile sort of precipitation events that I wanted to highlight as well. So as expected, windward basins are wetter, higher discharge, higher precipitation. Clearly, as precipitation increases, discharge increases. There's a lot of variability, obviously, between that relationship, and a lot of that has to do with differences between runoff efficiency between different events. But it would seem, looking at this, that the 2021 was not particularly anomalous at all. It generally follows the predicted trend of increasing discharge with increasing precipitation. The only places where there might be anomalous, slightly anomalous, is the Tulameen, which had a relatively high runoff efficiency of 0.7. The cold water as well, where it had a fairly high runoff efficiency. The other thing that's interesting is there seems to be, if you squint to perhaps look at the graph, there's almost two regimes, particularly in these leeward basins, where you have sort of the high precipitation regime that follows these blue lines, and then you have sort of very high runoff efficiency regimes, where you have high runoff efficiencies, high discharge for very modest amounts of precipitation. Not something I fully understand yet, but something that would be interesting to look into. But looking at this graph and sort of summarizing it, the answer we have is 2021 was not beyond what would have been expected, I guess, for the amount of precipitation that was delivered by the atmospheric river event. And in that respect, weren't perhaps that anomalous, and were maybe just primarily driven by precipitation. Lastly, some streamflow return periods. Highly variable. We have return periods. We're looking at gauges all the way from the South Island, well into along the lower mainland, and then leeward into the Similkameen Basin. We have quite a wide range of return periods. I should point out that for many of these sites, the streamflow event associated with this atmospheric river was the event of record. The highest event experienced. A number of events were at least a 1 in 20-year event. Several were 1 in 50, and at least 5, mostly again leeward of the Cascades, were 1 in 100-year events. There's a couple of reasons for the large spatial variability. One is hydrologic processes themselves can be quite heterogeneous in space. The other is we're estimating return periods by fitting GeV frequency distributions, and the record lengths are not consistent at each of these gauges. The data themselves are provisional. The 2021 event itself caused quite a considerable, in many locations, just destroyed gauges. So that data is not available. But in a lot of other sites, there was a lot of changes to the channel geometry, which affects the rating curve, which is used to estimate discharge. So a lot of the discharge values themselves can have high uncertainty. And then to conclude, really quite simple. Runoff is generated by what we would call a rain on snow event, likely conditioned by a wet fall, but arguably precipitation was the dominant factor for the extreme streamflow that was experienced. Many locations experienced an event peak flow greater than any value in the prior station record, and many of those were over a 1 in 100-year event. Thank you.
Great. Thank you so much, Marcus. Oh, apologies. My name is Ashley Jollymore. I'm taking over from Nathan to convene this session. So thank you so much. That was such a great talk. We have a few minutes for any questions. If we do have questions, we can put it in the chat. I'm just going up. Apologies. I guess I do have one question, and it's kind of more of a comment related to the sensitivity of the amount of snowmelt that goes into the runoff for these types of events. And it's kind of a comment or question about how can we understand the relative amount of melt before we go into these type of events, given that sometimes a less isothermal snowpack will absorb quite a bit of water. How can we understand those dynamics before we go into an event such as this one?
Yeah, it's really understanding two things: the amount of precipitation, potentially how much the temperature is forecast to increase, and what the freezing level would be for that particular storm. But I guess the other issue is maybe if there was some way to monitor the condition of the snowpack itself, whether the snowpack is deep and cold and therefore can absorb a lot of rainfall, or whether the snowpack is what we call ripe, in which case it's essentially warm and wet and therefore has no capacity to store moisture and will itself become a source of moisture. So, I mean, it's potentially monitoring or modeling or some combination of the two to understand not just what the atmospheric river, what conditions the atmospheric river will bring, but what is the state of the snowpack itself, and whether it will be a source or a sink, really.
Yeah, that's a great point. So we have a question here from Trevor Murdoch. So does this mean that the antecedent precipitation was not necessarily very important, or is it possible that it didn't drive any additional stream flow, but could have mattered in terms of stream flow landing in places that were already wet? And I think that's precipitation landing in places that were already wet.
Yeah, I would agree that maybe in places like the CMOS, where, well, in the CMOS, it is, I mean, there's probably two things that drove that flooding. Was, I think, the Nooksack was flooding, but as well as poor drainage due to the fact that the soil was probably wet. It's the details are difficult. I think obviously the atmospheric river, the precipitation was the driving force. Whether or not the difference between a 50-year event, a 100-year event could very easily be down to the details like antecedent precipitation or snowmelt contribution. But I guess the point I was trying to make is the main driver is precipitation. It's not to discount that antecedent conditions weren't important or that snowmelt wasn't an issue. It was, but and that might explain the spatial variability between different locations as well.
Yeah, that's great. So thank you so much. Oh, there's one from Mindy. We do have a couple of minutes. Just to note that our next talk is going to be at 8:20, or excuse me, 9:20 Central Standard Time. So there's 5 minutes here. We do have a question. If you need to take a break, though, please do so, and we'll reconvene in 5 minutes. But a question here from Mindy: how well do you think we know the record in river flow if we have so many overflow and gauges destroyed, rivers filled in or eroded? Any way you think we can improve our discharge data?
Really would have somebody from Water Survey answer that question, but I think it is challenging. It's recognized that for these extreme events, it's very difficult to get accurate measures of stream flow. We're dealing with parts of the rating curve that have to be extrapolated well beyond observation. The changes in the channel themselves may invalidate the rating curves. So I don't know how to solve it, whether it's some form of hydraulic modeling or going in there and understanding how changes in the cross section affect the rating curve. But yeah, it does add uncertainty. I myself, not sure how you would overcome that entirely. It's maybe just understanding what the uncertainty is and doing a better job perhaps of finding locations where gauges are more robust to these sort of changes or these higher stream flow conditions. And there may be novel ways of measuring stream flow that maybe for someone from Water Survey could perhaps they're more aware of.
Yeah, I think that's great. We also heard from BC Hydro yesterday too about some good non-contact ways of trying to measure peak discharge as well. So yeah, definitely a trouble. A question here from Ruping. Again, a note to everybody, we're technically on break. We have 4 more minutes until the next talk, but so take a break if you need it. A question here from Ruping. The antecedent conditions are also time sensitive. How do you handle this?
If I understand the question correctly, the API antecedent precipitation index is sort of designed to handle that. And what the API is you can think of it as a weighted average with an exponential decay. So the API is most affected by precipitation on the previous day, and then the weightings decay exponentially as we get further and further back in time. So the idea is the recent precipitation is the most important in terms of conditioning API. And we use, or I use base flow recession as sort of an idea of understanding what sort of API timescales and what API constants to use. So the characteristics of the watershed themselves in terms of shedding water over the long term from the soil as sort of a way of tuning that parameter. I'm not sure I answered the question, but I answered as I understood it.
Yeah, I think that's, and if Ruping has a follow-up, you can also unmute yourself. Oh, he says thanks, so I assume. And there's a comment here from Liza. Marcus, you're kind of getting bombarded because we're in our break time, so I apologize. We're taking this time to do a bit more questions. Earlier question, Francis reminded that they looked at, oh, I think this is in regards to a previous
Yeah, it was
question.
It was for the question which Mindy asked for my talk. Sorry about that.
Yeah, no problems at all. So I think with that, we do have 3 more minutes until the next talk. So we will take a bit of a break here and reconvene then in 3 minutes. That's 9:20 Central Standard Time. So go take a break. We'll see you in 3 minutes. Okay, everybody, it's now 9:20 Central Standard Time. We'll get started then on the next talk. So the next talk is from Chia-Hung Sun. Dr. Sun was a postdoctoral scientist with the Pacific Climate Impacts Consortium. And I've just, Francis just let me know that Dr. Sun is actually in China right now and will be taking a position at the Nanjing University for informational science and technology. So congratulations, and we'll get started with your talk, Dr. Sun. If you could share your screen too.
Yes. Yeah. Can you stop your sharing and then I can? Oh, yes.
Oh, perfect.
Okay. Thank you for as this introductions. Hi everyone. Today I'm also talk about 2021 BC flood event. I will quantify the human influence on extreme stress flows in 2021 BC flood event. In November 2021, a powerful atmospheric river met landfall and blew 2 days of extreme precipitation, and that led to floods and landslides in the southwestern BC. All roads between Vancouver and the rest of Canada were cut off. Oh, sorry. In the second figures, according to the observations, this figures is same as the Marcus has shown. Peak river flows at many stations have except atmospheric except historical records. Among the 32 regulated stations, 20 stations experienced at least 1 in 20 year event. 11 stations experienced at least 1 in 50 year event, and 5 stations experienced more than 1 in 100 year event. So it is important for us whether human influence climate changes influence the occurrence of the this flood events. So these studies we will quantify how has human caused climate changes influence the likelihood and the magnitude of such events. We will compare the magnitude of the likelihood of extreme stress flows under different climate states by using the large ensemble simulations. So for data, we use the Danish Streamflow simulators using the weak GL model. This hydrologic model was driven by the KM2 large ensemble, and the KM2 large ensemble is fostered by the CMOS forcing and fostered by the RCP 8.5 scenarios up to 2005 years. KM5 large ensemble provides 50 ensemble members, and weak GL model is coupled to the glacial model and noticed with R weak to achieve the stream flow data. And the daily values of minimum temperature, maximum temperature, and precipitation have been statistically downscaled to the resolutions of hydrological model. This is about 0.0625 degrees. Here we extract the maximum daily stream flow in fall season. It's the October, November, December for each year and each model run of the large ensemble. And the study period, we focused on the earlier 20-year period, 1950 to 1969, and the current period, 2011 to 2030 period. So since the hydrological projection for 5 ensemble members could not use due to the incomplete spatial coverage, here we only use the 45 ensemble members in our studies. So we in each period we can have 900 symbols for next step study. We know the designs of roads, bridges, and other structure often requires estimate the peak flow quantities that correspond to return period varies from 2 years and up to perhaps 200 years. So when we use a smaller symbol size to estimate peak flow quantities, such as observation data, this quantile often corresponds to return periods that are larger than the sample. So using the benefit, using the large ensemble simulations, we can have enough samples to robust estimate the return level periods, different return periods values. In this study, we use the empirical method to estimate 2, 5, 10, 20, 50, 100, and 200-year return levels during the 1950 to 1960 1969 period and 2011 to 2030 period. And we use the bootstrap method to construct the 90% confidence interval for each quintile. And then we also estimate the frequency changes in exchange strength flows. So here we use the risk ratio to compare the relative frequency changes in current periods and early periods. We use the 20-year events and 100 events in the past periods and the different events, because in the introduction stations, we also showed in observations the 2021 DC events at the most station. The observation shows the event can be up to 20-year return levels, and some stations can be up to 100-year return levels. So we use the two events return level. Here we show the flat frequency results for 7 locations. They are regulated located within reservation and have drainage area greater than 285 kilometers square. The figure shows location of stations we show. Here is our result. Here is our results. The figures show the frequency, flat frequency results for the 1 location in the cold water river basin. The black line and shadow represent the best estimate and the 90% confidence interval of flux magnitude for different return periods during the 1950 to 1969 periods. And the blue one indicates the results for the 2011 to 2030 periods. And we can find it is very obvious that the simulated flux magnitudes for all return periods in the current climate are larger than in the 1950 to 1969 climate state. And we calculate the relative change of the magnitude of 100-year events in current period related to the past period. The results show as the number in the upper left corner. In these locations, the best estimate of 100 for the peak float in the current climate is 54% larger than those over the 1950 to 1969 period. And so when we look other stations, we also find a similar results for the 6 locations in 4 different river basins. We can see for all returnable events, the magnitude in the current periods are higher than the past period. And the best estimate of 100-year for the peak float in current climate are 16 to 63% larger than those over the 1950 to 1969 period. The values may vary with locations, but shows the similar results. Now we would like to look at the changes in the likelihood of extreme strainflow. The blue points an arrow bar represent the best estimate and 90 constant interval of risk ratio for 20-year events, and the black index results for the 100-year events. We find that for events with the magnitude of the 20-year for the peak float in the 1950 to 1969 climate, the ratio of its probability in the current climate compared to the 1950 to 1969 period, the risk ratio is 1.5 to 2.5. And for an event with the magnitude of 100-year peak float, the ratio of probabilities, the risk in the current period is 2 to compared to the past period is 2.2 to 4.3. The values vary with location. Besides, we also find at all locations the lower bound of 90% constant interval of the risk ratio is greater than 0. So we can say there is an increase in the likelihood of the event in the warmer climate state. So the results tells us that the 100-year for the peak float in the 1950 to 1969 climate now can happen 2 to 4 times as frequent due to the influence of human-induced climate change. So extreme strainflow like BC 2021 November events can happen more frequently. Besides, the risk ratio of 100 events is higher than at 20-year events at all stations. The results tells us that the relative frequency increase tend to be larger for more extreme events than for weak events. So we have some conclusions. So human-induced climate change increase the magnitude of peak float and can increase the frequency of extreme strainflow events. The probabilities of 2021 BC extreme strainflow events are 2 to 4 times as large as they were in the 1950s as a result of human-induced climate change. There is some indications that the more extreme events increase in frequency more rapidly with warming than these extreme events in the large ensembles. So the 1 in 20 and 100 extreme events is guides the designs of infrastructure. So our results show they will happen more frequently as well as more intensity. So we need to adapt the infrastructure to reduce the risk of damage. This is the presentation for me. Thank you.
Great, thank you so much. That was wonderful, scary, but wonderful. So we'll have time for one quick question. Very nice study from Ruping Mo. By human influence, CO2 increase must be the main factor. Do the climate models also include other factors such as urbanization, human-induced wildfires, and deforestation?
I think we didn't consider much about nations, but we in our studies some research other researchers they consider the wildfires, and the wildfires may influence the currents of the BC flood events, but based on the data we don't have much very sure conclusions for it. So I think for this for this follow study should be required. And yeah.
Great. Well, thank you very much. If there's any additional questions, they can also go in the chat. And Dr. Sun will answer them there. So thank you so much. We'll go on to our next presentation. Our next one is a familiar face, Dr. Nathan Gillett. He's a research scientist with Environment and Climate Change Canada at the Canadian Centre for Climate Modeling and Analysis. So take it away, Nathan.
Thank you very much, Ashley. So yes, I'm going to be talking, you will have seen much of the contents of this talk already, since I'm going to be describing a study which I kind of led and coordinated, but for which other people which you've already seen speaking did the analysis. So you can see the list of authors here. So there was a big team that we kind of convened to do a rapid attribution analysis shortly after the event. And then we published a preprint in January, and then we have a paper out from April describing the results of this study. Sorry, I'm having a problem advancing my slides. Okay, so my intro slide, I think probably no need to go over this material. We've seen and we've had a lot of great presentations in these sessions yesterday and today, describing the many impacts of this event. So of course it was a very impactful event in BC, you know, the costliest natural disaster in BC history. So as I mentioned, we carried out a rapid attribution study, looking at multiple aspects of the event, from the atmospheric river itself through to the effects on precipitation, and then through to the impacts on streamflow, or the effects on streamflow. And we looked at how large and how unusual was the event in these variables, and then how has human-caused climate change increased the likelihood and magnitude of extreme events in each of these variables. And there on the right is the paper describing the results of this analysis. Okay, so we've seen also a lot of pictures like this already. These are a few more. These are from the BC Ministry of Transportation and Infrastructure. That one up on the top left is the Coquihalla Highway on the Coldwater side. So going towards Merritt, you can see big impacts there. There wasn't, certainly not just one bridge out on the Coquihalla. There was many impacts both on the Coquihalla side and on the Coldwater side. The top right there is the Sumas Prairie area in the Lower Mainland. The bottom left is near Lytton. You can see impacts there on the Highway 1, Trans-Canada Highway, as well as railways. And we've heard already that all rail links and all highway links between Vancouver and the rest of the country were severed during the event. I'm talking to you from Victoria, BC, which is on Vancouver Island. You can see that we had some impacts here as well. The bottom right is Highway 1 near Victoria. Okay, so like I said, you will have seen a lot of the results in this talk already. I'll highlight, but I will try and highlight a couple that we haven't yet covered. Okay, so starting with the synoptic situation, and we have heard a lot about this already. There was an atmospheric river with an axis determined by the low pressure to the north, high pressure to the south, which pumped a large amount of moisture into BC. And we've heard already how the alignment of this atmospheric river was more westerly than usual, than typical for other atmospheric rivers impacting the region. And we're suggesting here that, well, that the circulation aligned with the Fraser Valley, funneling moisture into the region. Kent Moore yesterday, I think, also pointed out that that westerly orientation means that the Lower Mainland isn't in the rain shadow of the Olympic Peninsula. So yeah, I think it's kind of debatable whether it was, you know, the alignment with the Fraser Valley, or whether it's just that the moisture was not traveling over the Olympic Peninsula with a more westerly orientation. But certainly these factors together tend to bring more moisture into the eastern part of the Fraser Valley. So yeah, the figures on the right is is column water vapor. You can see going from the 13th, 14th to the 15th of November, you can see the characteristic atmospheric river. The arrows are integrated vapor transport, which is the variable used to define atmospheric rivers. And the purple box here is, that's our study region. Okay, so this analysis of the atmospheric river itself, this was done by Alex Cannon. He didn't actually cover this in his talk, so I will describe this a little bit now. So if we just think of, if we just look at IVT, integrated vapor transport, averaged over that rectangular box, the atmospheric river event in 2021 was about a 1 in 3 year event. So, you know, I mean, strong for the year, you know, and not something that happens quite every year, but certainly not a very extreme event based on that metric. The figure at the bottom right shows the total integrated vapor transport for the strongest storm of every year. You can see that just if you look at the height of these bars at the bottom right, 2021 was not particularly unusual. But if we focus particularly on just the westerly events, okay, so now if you turn your attention to the figure at the top right, this shows the orientation of atmospheric river events affecting Southwestern BC. You can see that most of them come from a southwesterly direction, but the 2021 event, which is shown in blue, was more westerly oriented than typical for this region. So we've heard this already yesterday, but this is just showing this based on this analysis from Alex. And so if you look again at the bottom right figure, if we look just at the blue dots now, that's the strongest westerly event of each year. So 2021 was a bit more unusual on this measure. So if we look at just westerly events, the return period was about a 1 in 12 year event. So, you know, unusual, but not really exceptional. Just looking at the figure at the top left, this is a time series of integrated vapor transport. You can see the area shaded in gray is the time from 0Z on 14th of November through to 0Z on the 16th. So it's the 14th and 15th of November when measured in UTC. And that was really when this event occurred, and also when the precipitation occurred. Incidentally, if you go use UTC days, then it falls very nicely on those 2 days in particular. In local time, I think it extends also onto the 13th. Excuse me. So this slide is looking at an attribution analysis of the change in integrated vapor transport. And again, this is Alex's analysis. The figure on the right shows annual maximum storm total integrated vapor transport. So again, this is the measure used to define atmospheric rivers over that box in southwestern BC. This is from a large ensemble of CANAR CM4, so regional climate model simulations. And this model has been shown to represent atmospheric rivers in the region well. You can see it's plotted here as a function of the global mean surface air temperature in these simulations which run into the future under a scenario of increasing greenhouse gas emissions. So you can see that total integrated vapor transport for the strongest storm is increasing with global mean surface air temperature. The dark blue lines there show the fit of a GEV model with several of the parameters depending on GMST. And you can see that they are a good fit to the data, and they show an increase in the TIVT with the global mean surface air temperature. So based on this fit, for a 1.09 degrees Celsius global warming to date, human-induced climate change is estimated to have increased the probability of AR events like the 2021 event by 64 to 93%. So the analysis was that human-induced climate change had increased the probability of events, AR events like the one we saw, by, like I say, 60 to 90%. So not quite doubled, but still a substantial increase in the probability of this kind of event. thinking about the future, if for a 3 degrees Celsius warming, which is relative to pre-industrial, the probability of this kind of event is projected to increase by about 300%. So under this level of warming, 3 degrees warming, a substantially larger increase projected in the future. Okay, so now I'll turn my attention to precipitation. And again, you've seen some of these figures before, well, probably pretty much all these figures before. So that figure at the top right, that's the Kappa analysis, the 2.5 kilometer Kappa HRDBS analysis, and that's precip on the 14th and 15th of November using UTC days. And so based on this measure, you can see that the highest precip occurred, okay, and the circles here are the gauges. In terms of the gauges for this period, the highest recorded was at a station here in Southwest Vancouver Island of over 300 millimeters. You can see, as we already have seen, that there was also very high precip, in the Fraser Valley and in Hope in particular. Based on the Kappa, there was even higher precip in the mountains, kind of north of Abbotsford. In this data set, even over 400 millimeters in that 48-hour period. But as Lisa showed, we can look at also the time series of the precip averaged over this box of RX 2 days, so the maximum annual time series, maximum annual 2-day precipitation averaged over this box. So the blue is ERA 5, the brown here is Kappa. As we heard already, it was an extreme, it was the record event in the, sorry, this is the 10-kilometer Kappa now on this time series, because the 2.5 kilometer Kappa only started in 2016. So based on these data, you can see that it was a record event in Kappa, although it wasn't a record event in ERA 5. And yeah, as we heard already, it is substantially more extreme in Kappa than the 2021 event was substantially more extreme in the 10-kilometer Kappa than in ERA 5. It was about a 1 in 100 year event in Kappa versus about a 1 in 50 year event in ERA 5. So yeah, I think we've heard some discussion already about these differences between Kappa and ERA 5, and I think Lisa addressed, and I mentioned in my question earlier in the session, if you look at the earlier years, the Kappa annual maximum 2-day precip seems to generally be lower than ERA 5, but in 2021, the Kappa is substantially higher than ERA 5. So yeah, the Kappa is higher resolution, it's 10 kilometers versus about 25 to 30 kilometers in ERA 5, but that didn't mean that it was higher, it simulated higher precip in these previous years. I'll show you now also some maps of that 2-day precipitation in these different data sets. So on the left there is ERA 5 again, and on the right, and we've seen also similar plots to this, I know yesterday from Kent Moore. On the right is the 10-kilometer Kappa, and then the 2.5 kilometer Kappa. You can see, of course, as you would expect, the higher resolution products match the gauges better. They also, as I already said, seem to simulate an overall higher amount of precipitation, with the precip for this event somewhat underestimated in ERA 5, it looks like. But yeah, as I mentioned, I think there probably is still more work that could be done to try and understand why the event was substantially larger in Kappa than ERA 5 for this particular event, whereas in previous other extreme events, you know, we don't see that discrepancy between Kappa and ERA 5. So I don't have an answer on that, but that's just pointing out that there is that difference. Okay, so moving on to the attribution, and Lisa showed this analysis already in her talk, but just to kind of reiterate, human-induced climate change is estimated to have increased the probability of precip events at least as large as that observed in 2021 by a best estimate of 45%. And you can see that by comparing the area to the right of the red line on the green histogram versus the kind of orangey brown histogram. yeah, and Lisa already described this. It was based on 22 Synoptic models, 166 simulations. So again, kind of in the similar ballpark to the estimate for the atmospheric river, the estimate is that our analysis shows that human influence increased the probability of an event at least as strong as the 2021 event. The best estimate is around a 50% increase in that probability. Under a scenario with 2.7 degrees Celsius warming, so that was the SSP 245 scenario at the end of the century, this increase in probability is projected to be around 200%. So substantially larger increases in probability of this kind of event projected in the future under stronger global warming. Okay, and I think we've seen this figure too quite a few times, so I won't dwell on it too much, but just to point out that, as has been said already, it was certainly wetter than average prior to the event. So if we look at the 13th of November, just before the event itself, it was already certainly one of the wetter years so far. So again, this is showing cumulative precipitation from the start of October in era 5. Lisa already talked about the antecedent precipitation index, which is shown on the right, for which this was in this data set was the strongest event if you calculate API including the event itself. Okay, but I think I'll move on now, since we already have had a lot of discussion about how it was already a wet year prior to the event itself. Okay, so moving on to Streamflow, and this is work that Marcus did, and he discussed it in his talk, but again, I'll just summarize it and then highlight a couple of things which haven't been covered up till now. So yeah, the Streamflow was especially towards the east of the area was rarer, over a 1 in 100 year event at some of these locations towards the east of the basin. As Marcus already said, the peak river flow at many stations exceeded historical records by a large margin, a number of these stations. And just to reiterate again that this data is provisional, that there were the damages to the gauges, and there were changes in the river channel which affect the rating curve. So, but I guess just one point to kind of highlight from this is that at least for parts of the basin, streamflow was even more severe, even rarer than, had a larger return period than precip. Okay, this is something that hasn't been touched on yet, so I'll just describe these results in a bit more detail. This also was included in the paper. This analysis was done by Megan Kirkmeyer-Young. So yeah, as we've heard, there have been a number of wildfires in the area affected by the flooding over the last few years, and particularly in 2021 when there was a lot of wildfire in southern BC. So the map that you can see at the top right shows wildfire perimeters over the last 6 years. The red color there is 2021. The box there, that quadrilateral, that's our study area for the flooding and the precip. Oh no, sorry, it's a different study. It's a different study area that we were using for the highway. Yeah, apologies for that. But okay, you can see that there have been a number of wildfires in the area in 2021 in particular. But okay, so the figure in the bottom left is now showing return periods for streamflow in the circles. Those are shown in those blue circles. We can look at, so for a particular gauge, we can look at the drainage basin upstream of that gauge, and then we can calculate the fraction of that basin which burned in 2021. That's what's shown in the colored shading there. So you can see that, for example, for the cold water basin draining towards Merritt, there was something like a 15% of that basin was burned in 2021. And I mean, just to get back, so we heard a lot of, in the kind of public discourse around the event, there was a lot of discussion of the possible role of wildfire. We know that, you know, burn scars do affect the drainage properties of the surface, and that, you know, we expect that the runoff is more rapid in burn scar areas. So there is, you know, there is a reasonable expectation for why we might expect these burn scars to have an effect on the runoff. Okay, and like I said, there was some area burn. So, well, there was about 15% for this this cold water basin draining to Merritt. You can see that there was somewhat smaller, but there was some fraction of the area burnt for these other simultaneous basins. But there was almost no area burn, for example, in the Coquihalla Basin or in the CMOS Basin down here. So yeah, so at the bottom right over here, we're in panel C, I'm showing the Streamflow return period against the percent of area burned in DC. You can see that there's no, I mean, the thing is, it's a very small sample. Probably we should, well, we only have a limited number of basins where we've got the Streamflow measures and the estimates of area burn. But there's no relationship obvious, or you know, there's certainly no significant relationship here between the percent of basin burn and the Streamflow return period. And so, yeah, it's a small sample, but you know, based on the data we have, we don't see a relationship between the runoff return period and the percent of basin burn. Okay, now I'll just go on to show Cao Hong's analysis of the attribution of Streamflow. So human-induced climate change is estimated to have increased the probability of extreme Streamflow events by a factor of 2 to 4. That's the best estimate. And based on these BIC hydrological model simulations, Cao Hong already showed this figure. So the blue is okay. So yeah, the blue is peak Streamflow as a function of return period for the present climate, and the black is 1950 to 1969, which we're using as a kind of quasi pre-industrial period here. So you can see that the peak Streamflow for a given return period has increased across all these basins. The risk ratio for a 100-year event is shown on all of the panels. It varies, like I said, between about 2 and 4. So that's the how much more likely a 100-year event is in the present climate compared to in the pre-industrial or in the 1950s climate. So those risk ratios, one thing I'll just draw your attention to, those risk ratios do seem to be higher for runoff, for peak Streamflow, versus the risk ratios that we were getting for the atmospheric river and for precip, which were more like around 1.5. So the next slide I'll show you, these are just, this was not in the paper, this is just some kind of preliminary results analysis done by Cao Hong as well. And this is looking at the snowmelt contribution to a high runoff risk ratio, or the possible snowmelt contribution to a high runoff risk ratio. So what's shown in the plot at the top right is the, so if we look at snowmelt averaged over drainage basins, and we pick the 2 days with the highest snowmelt, that's what Cao Hong here is defining as SX2 day. And then we can look at, for a 1 in 50 year event, I think she was looking at here, how the probability of this kind of event has changed in the 1950s compared to the present. So is there, you know, a higher risk of a high snowmelt happening now? And again, this is in these BIC hydrological model simulations. So you can see that for most of the basins, there is indeed a higher risk of rare snowmelt events or a high snowmelt events in the present climate compared to the 1950s. In terms of kind of understanding this physically, you can think of if you have maybe a high cold mountain basin and you warm the climate, then you're more likely to get snowmelt events. On the other hand, if you had a low elevation basin which didn't have much snow to start with, then if you warm the climate, you might then just move into a regime where you have no snow and you have a lower risk of high snowmelt events. And that's kind of what's, if you look at the panel to the bottom right, this is just plotting this snowmelt risk ratio against 1950 to 1969 TASMAX OND. So yeah, I should just mention this is all for the October to December season. But you can see that these risk ratios are higher for colder basins, and they're tending towards 1 or even below 1 for the warmer basins. So that is consistent with this idea that for the higher, colder basins, with climate warming, we're seeing an increased risk of snowmelt, which may contribute to these higher risk ratios for runoff in the VIC model simulation. So I think, like I said, these are preliminary results, and I think there's more work to do to understand this. But there's some indication there that snowmelt, so with climate warming in this particular season for these particular basins, that we might also be getting a signal from climate warming increasing the risk of high snowmelt events. Okay, so moving to the conclusions, the rarity of the November 14th, 15th event. So for an atmospheric river, a westerly atmospheric river event, it was about a 1 in 10 year event, 2-day precip, depending on which data set we look at, about a 1 in 50 to a 1 in 100 year event. Streamflow varied across the area that we looked at, and it's preliminary data, but it exceeded a 1 in 100 year event in some locations. And like I said, we didn't find a relationship between the fraction of the basin burn and the streamflow return period based on available data. And just to reiterate, for the Nooksack and Sumas basin, there was no appreciable area burn in 2021, and the same for the Coquihalla basin. So for those basins where a lot of the impacts occurred, we know that it wasn't due to wildfire in 2021. There was, like I said, there was some area burn in other basins like the Coldwater. There's a possible contribution there, but in terms of the data, we couldn't see, based on the small sample available, we couldn't see a relationship between the fraction of basin burn and the stream flow return period. Human-induced climate change substantially increased the probability of the atmospheric river event and the resulting precipitation and flooding. And such events, including the atmospheric river, extreme precip, and the flooding, will become more likely in the future with additional warming. And as I said, you can read the study there in Weather and Climate Extremes. Thank you.
Great. Thank you so much, Nathan. That was great. So just a note for everybody, if you have questions, to put them in the chat. We do have one or 2 minutes for questions. So if you do have a question, there's one about the reanalysis era 5 susceptible to a drizzle problem, but I believe that might have been answered. I do have one question, the snowpack and the snow pillows, that risk ratio slide that you show, whether temperature was a better indicator than elevation, or if you did look at that in terms of the snow pillow elevation.
Yeah, okay, good question. I think for that analysis, I think we just looked at temperature rather than elevation itself. I mean, physically, we did see, and Calhoun kind of pointed this out in some, not in her talk, but she kind of noticed that there was this non-monotonic relationship between warming and these SX2D, these extreme snowmelt events, and that if you start from a cold basin, you warm the climate, you get more of these extreme snowmelt events. But if you keep warming, you get to a point where then there's just no snow there climatologically, and then of course you get fewer of these extreme snowmelt events. So I think that she has done the analysis comparing to temperature, but not to elevation. Although physically, I would expect that the elevation and the temperature are kind of closely linked. So probably there would be a similar relationship with the elevation.
Yeah, interesting. So there was a question about the 1950 to 1969 reference period, whether that was used for, why that was used for Streamflow. Francis did answer that the ensemble started in 1950, but if you have any additional comments on that, Nathan?
Yeah, so that's correct. Of course, the simulation started in 1950. I mean, we do know that well, the estimated human-induced climate warming to the 1950s is something like 0.2 degrees Celsius compared to about 1.1, at least 1.1 degrees to the present. So it's not quite pre-industrial, but it is, you know, most of the way there.
Great. Yeah, that's great. So with that, we've reached the end of our talks. I wanted to thank all of the speakers for today. It's such a great session and some really, really amazing talks. So thank you so much. I just also wanted to put in a small plug. So there is a panel discussion happening today responding to the BC extreme events panel discussion. This is happening at 12:55 Central Standard Time. So really want to encourage everybody to attend what will be a very, very interesting panel discussion. So with that, I want to thank everybody again, especially our speakers, and we'll see everybody at the panel discussion.